The universe is a vast cosmic stage filled with countless stars and planets. But hidden deep within its darkness lie some of the strangest and most mysterious entities of all. Black holes, objects that can swallow light, bend time, and shake our understanding of physics to its core. So what exactly is a black hole? How does it form? Is it dangerous? And could a human ever fall into one? Let's find out. A black hole is a region of space where gravity is so strong that nothing can escape from it, not even light. In other words, a black hole is an ultra-dense, ultra-massive object that warps space and time around it. If you get too close, you will never be able to escape, whether you're a beam of light, a spaceship, or any kind of matter. The point of no return is called the event horizon, an invisible boundary that marks the line of no way back. Most black holes are born from the death of massive stars. When a star more than about 20 times the mass of the Sun runs out of fuel, it undergoes a supernova, a gigantic explosion that blasts its outer layers into space. The remaining core then collapses under its own gravity. If this core is massive enough, it shrinks into a point with infinite density and almost zero volume, called a singularity. At that point, all the laws of physics as we currently know them break down. Not all black holes are the same. Based on their mass and how they form, scientists classify them into three main types. Primordial black holes may have formed right after the Big Bang, much smaller than typical black holes. Still hypothetical, no confirmed detection yet, but a very intriguing idea. Stellar black holes, formed from the collapse of massive stars, have masses from about 3 to a few dozen times the mass of the Sun. Supermassive black holes, found at the centers of most galaxies, including our Milky Way. Masses range from millions to billions of times the mass of the Sun. Example: Sagittarius A*, the supermassive black hole at the center of the Milky Way. There may also be intermediate mass black holes, with masses between stellar and supermassive black holes, but they remain quite mysterious and harder to detect. When matter, gas, dust, or even entire stars gets pulled toward a black hole, it doesn't simply disappear immediately. Instead, it spirals around the black hole in a structure called an accretion disk. In this disk, matter is compressed and experiences intense friction. Temperatures can reach millions of degrees. It emits powerful X-rays and visible light, which we can detect with telescopes. Once matter crosses the event horizon, there is no turning back. It is lost to our universe. At least from the perspective of an outside observer. We can't see black holes directly, but we can detect their presence by observing their effects on their surroundings. Stars orbiting an invisible object. If a star appears to be orbiting nothing, that nothing might be a black hole. X-rays from the accretion disk, hot, infalling gas emits high-energy radiation. Gravitational waves, ripples in space-time created when two black holes collide and merge, first detected in 2015 by LIGO. A major milestone came in 2019. When scientists released the first ever image of a black hole's shadow in the galaxy M87, a historic turning point in astrophysics. According to Einstein's theory of relativity, gravity can warp spacetime. This means that time flows more slowly near a strong gravitational field, such as near a black hole, compared to farther away. If you were to stand near a black hole for some time and then somehow return to Earth, only a few minutes might pass for you, while years could have passed on Earth. This kind of time dilation is not just science fiction like in Interstellar. It's a real effect predicted by physics and confirmed in weaker forms, for example, near-Earth and GPS satellites. Short answer: nothing good. If you fell feet first into a black hole, you would experience a process called spaghettification. Your body would be stretched out like a strand of spaghetti due to the extreme difference in gravitational pull between your feet and your head. You would be torn apart at the atomic level long before you reached the singularity. And once you cross the event horizon, all information about you is effectively lost to the outside universe, at least according to our current understanding. In quantum mechanics, information cannot be destroyed. But when matter falls into a black hole, all visible information about it seems to disappear. This creates the famous black hole information paradox. Stephen Hawking proposed that black holes can emit radiation, now called Hawking radiation, and slowly evaporate over time. But does that radiation carry information? Or is information truly lost? No one knows for sure. This remains one of the biggest open problems in modern physics. Some theories suggest that black holes might be connected to white holes or form wormholes, shortcuts through spacetime. If true, a black hole could potentially act as a gateway to another region of the universe, or even a bridge to an entirely different universe. However, these ideas are still speculative. There is no experimental evidence yet. And even if wormholes do exist, we currently have no technology to safely test or use them. For now, these remain fascinating possibilities at the edge of theoretical physics. Scientists estimate that the Milky Way alone may contain hundreds of millions of stellar black holes. Most large galaxies have at least one supermassive black hole at their center. Since the universe contains hundreds of billions of galaxies, the total number of black holes could easily reach trillions upon trillions. In theory, if you compress enough mass into a sufficiently small region of space, you can create a black hole. Some physicists have speculated that high-energy particle colliders like the Large Hadron Collider, LHC, might create tiny black holes. If they do form, they would be microscopic. They would evaporate almost instantly via Hawking radiation. They would not pose any danger to Earth. However, creating and controlling a real macroscopic black hole is far, far beyond our current technological capabilities. To better understand black holes, physicists use a concept called the Schwarzschild radius, essentially the radius of a non-rotating black hole, corresponding to its event horizon. In simple terms, if you compress an object inside a sphere whose radius is smaller than its Schwarzschild radius, that object will become a black hole. Nothing, not even light, can escape. Some striking examples. If the Sun were compressed into a black hole, its Schwarzschild radius would be only about 3 kilometers. If the Earth were compressed into a black hole, it would shrink to about the size of a pea. This shows that a black hole does not need to be physically large in size to be extreme. What makes it terrifying is the enormous mass packed into an incredibly tiny volume, which produces an unimaginably strong gravitational field. Black holes are not just light-eating monsters. They are symbols of the limits of human knowledge. They are regions where classical physics and quantum mechanics clash, where time is bent, and where information may vanish. Studying black holes doesn't just help us understand the universe better. It may open the door to an entirely new level of physics, possibly leading to theories even deeper than Einstein's. In a way, black holes mark the frontier of our understanding, the edge where what we know ends, and the great cosmic unknown begins.